So this is the title of my talk. It is Structures and Solids Without an Elastic Potential. And this is what I wanted to mention. All these people are very related to my research and very related to the things that I will present during the talk that I'm giving. So I would like to start with the technical part and mentioning, sorry, 1 second. Mentioning probably the first problem I worked on, the formation of shear bands in solids. And here we see several examples that I have encountered in my life. What is a shear band? The shear band is the formation of a thin layer of intense shear deformation, which emerge spontaneously during the deformation of a solid. We see here several examples. Probably the most interesting is this one, where we see one layer of intense shear in this case and two layers in that case. I'm trying to find the correct position where to speak. So I have worked on this problem for several years, and I can say something that after a long time of research, 30 years of research in this topic, there are still several problems which remain unsolved. And for instance, one of these problems which attracted my attention was the fact that the shear bands exist in a material, and how does it behave when it is impinged by an incoming elastic wave. To analyze this problem, we have introduced a model of shear bands. This model is requiring incremental nominal shearing stress along the shear band, continuity of the incremental nominal traction, so it is not a fracture, it is something different, and continuity of the incremental displacement component normal to the shear band. So using these three ingredients, we have to formulate a problem of a shear band in a body which is receiving a wave from far. And this is the main problem. We have a shear band which is inclined. This has been generated during quasi-static loading. And there is a shear wave which is depicted as a deck of cards coming and impinging the shear wave. We need the equations to describe the behavior of the material. The equations are the incremental equation of nonlinear elasticity, which depends on the state of pre-stress in the material. So, to analyze this problem, we need the green function for an infinite body, and this was obtained by us years ago together with Andrea Pico-Roth and John Willis. And then we need also boundary integral equations. To derive this equation, we start from the Betti identity. Betti was the friend of Beltrami, who is the big guy to which the medal is entitled. From the Betti identity, we can obtain a boundary integral equation for the problem of the shear band. And the velocity, the incremental displacement, is split into an incoming wave and a scattered field. So this is the boundary integral equation that we derived. It is not the only ingredient because our material is incompressible, and we know that the mean stress plays the role of Lagrangian multiplier. So we need a boundary integral equation also for the incremental mean stress, and we derived it in this way together with Domenico Capuani, another of my pupils, who is not here unfortunately. With these ingredients, we had to set up a numerical procedure. And we did not invent it. We used a proposal from Alberto Salvadori, who developed for fracture mechanics. We adapted the same procedure to shear bands. And then we had to implement a specific material model for the behavior of the infinite body containing the shear band. We have used the incremental equation by Biot, adapted to the so-called J2 deformation theory of plasticity. We can see here the stress-strain relations. It depends on an hardening coefficient, which might describe almost perfectly plasticity, n.1, or elasticity with n.08. So, putting all these ingredients together, we can analyze the response of a shear band to an incoming wave, and, for instance, we can plot the stress intensity factors at the tips of the shear bands, because the shear bands has a singularity at every of the two tips. And what we can understand from these graphs, we understand that the stress intensity factor strongly depends on the frequency of the wave. So there are peaks where the effect of the singularity is higher, and these peaks are related to the frequency of the incoming wave. We can also plot the fields. On the left side we have the scattered field. On the right side we have the total field. So what we see here, that there is an incoming wave sinusoidal in this direction, and a shear band is there waiting for the wave. And when the wave arrives, the shear band produces a scattering of many thin waves which remains almost parallel to the existing shear bands. So the shear bands perturbs a field that otherwise would be sinusoidal in this direction, but the effect is very important because it extends to the wall space where the shear band is located. The shear band is a spontaneous emergence of a discontinuity in the deformation rate. Now, I would like to ask myself if I can use the same concept in an apparently different situation. The situation is folding. Can we analyze the emergence of folding with the same machinery of shear bands? The answer is positive because of our definition of folding. In my view, folding is a process of localization of curvature. In the shear bands, we have a localization of shear. In folding, we have a localization of curvature. And so, this is bending, this is folding. What is folding is a highly localized bending. If we would enlarge the situation there, we would see something like that, but very concentrated near a point. So the machinery that we use for shear band can be easily adapted to localization of folding. Bending and folding can be spontaneous or man-made. On the left-hand side, we see bending, which has been formed spontaneously. On the right, we see bending formed due to our intervention. And the same thing can be said for folding. On the left side, we have spontaneous folding in rocks, in shells. And on the right, we have something made by us, forced by us. I'm interested in spontaneous folding, the condition when a solid spontaneously generates folding. To do this, I have worked with a Greek postdoc, very good one, Panos Gorgiotis, and our idea was to use a Coursera material, a constrained Coursera material, an orthotopic material that we used in extreme conditions. What I want to say, even shear bands are formed when the material is heavily deformed, heavily stressed. It is in a state of extreme deformation. So the same thing we have mimicked with Coursera material, selecting the parameters in a way that the material is close to the loss of ellipticity. So what does it happen? First of all, we see the regular case. We have a constrained Coursera material, orthotropic, infinite, and we perturb the state applying a concentrated force, vertical there, or a concentrated bending moment there. In the regular case, when we are far from the boundary of elasticity, we see almost nothing. Of course, we compress vertically and we see the formation of a sort of valley. When we apply the moment, we see a mountain and a valley forming, nothing special. But when we do the same thing near the border of ellipticity loss, then we found something completely different. We found spontaneous folding, which may be along a line or along two crossed lines. If we do the same exercise with the concentrated bending moment, we found something even more spectacular. We found the evidence of folding. It means that instead of folding, we have a true discontinuity in displacement. This can be calculated and has been evaluated by us analytically. This is speaking of solids, but I am a guy convinced that solids and structures are more or less the same things. All the times I found something in solids, I think I should replicate the same thing in structures and vice versa. So can we find folding in structures? Well, we did something that I see is very popular in this research group. We invented a microstructure for an elastic rod. The microstructure is made of quadrilateral elements with a spring and elastic hinges. So this is the clamped scheme compressed with an horizontal force, and this is a doubly supported scheme. How can this 4-bar element be realized in practice? Well, the idea is something like that. This is a sort of prototype. The quadrilateral element is made with a matches box, something which has a shear deformation, and we call it origami junction, because it's a sort of origami. Well, this is the main idea. What to do is, first of all, we have to sketch the deformation of the element and derive the equations. I have no time to derive the equation altogether, but we can do later if you wish. But anyway, the important point here is to notice that we have a micromechanical parameter, B over A, which represents the ratio between this length of the bars and the total length of the element. It's a dimensionless number. So we have the geometry, and we write down the equations for every element. So these are the discrete equations. The homogenization is immediate. Why? Because in the process when this element becomes of infinitesimal length, this guy simply becomes the second derivative of the angle theta, and all these guys become the function evaluated at the point. So our Reut theory is governed by two equations, a differential equation, which we see it here, and an algebraic equation there. So it's a system of coupled algebraic and differential equations, which cannot be detached. They have to be solved together. When we arrived here, I said, I'm not able to do anything at this level. But my student, a guy from Naples, Paradiso, Dr. Paradiso, because he had already his PhD, was able to manage to solve this, and actually he told me that this is a standard procedure because these algebraic differential equations are very well studied. And so what we have obtained, it's a generalization of a shearable rod. Here we see the Euler rod, and we see that the Euler rod can be obtained from two different theories of shearable rods. One theory is the Engesser theory is there, and the other theory is the so-called Harings-Reisner theory. So, reducing the parameters, both these models give the Euler rod model, unshearable rod, but I have to say that the two models are different, and our model is a generalization of the Engesser model, and reduces to the Engesser model when the micro-mechanical parameter A over B becomes equal to 1. Well, with the equations and with the model, we started studying the simplest problems that we could imagine. So the first is the Euler buckling of a clamped rod and the Euler buckling of a doubly supported rod. I don't want to enter into detail, but a particularity of this model is there are two sequences of bifurcation loads, which are separated by a critical load that we call transition load. And we can classify all the bifurcations for the continuous system and the discrete system. And one peculiarity is the shape of the bifurcation mode for transition, which involves here a faulting, so a discontinuity in displacement, self-emerging in the bifurcation mode for the clamped scheme. Something similar happens for the doubly supporting supported rod. And the transition mode now has also a strange shape. It's a bookshelf-like mode. So we take several books and we incline it like that. The thing that we did not expect, but it emerged from our model, maybe you may say, well, that's not too surprising because you have implemented an origami junction, maybe folding is already there. And in fact, we discovered folding. So this is a sequence of snapshots taken during the compression of a doubly supported rod. We see here the beginning of the post-critical behavior. This is at the middle of the post-critical behavior, and we see the formation of folding. So, and now I will show you a movie showing the compression of an elastic rod, doubly supported, and we will see at a certain point the formation of folding. This folding spontaneously formed. This is the method. This is the emergence of folding. And it continues. We have analyzed the theories for nonlinear behavior, so we can analyze huge deformations, even irrealistic. I have to say sometimes they become irrealistic at a certain point. We will see. Up to now, this behavior is stable. Now, at this point, it becomes unstable. There is a secondary bifurcation, and this deformation is unrealistic because it compenetrates and it is unstable. But nevertheless, we plotted anyway. And of course, we can compare the discrete model with the continuous model. And something interesting happens here, because the comparison depends if the elements, the discrete elements, are in an odd or even number. So if we look for even number, we see that the two deformations are simply superimposed. So the comparison is almost perfect. But things go differently if the number of elements is odd. And we see here two movies, parallel movies, comparing the odd number of elements below with the even number of elements. We see that at the beginning there is almost no difference. There is deformation, but there is a secondary bifurcation here in the discrete system, which is not present in the even system. The formation of folding, of course, and now we see that the odd system starts following a different path. And this different path is a manifestation of folding, because with an odd number of elements, the element cannot simply arrange like in that case, and start a tertiary bifurcation and behave progressively different from the continuous model. This difference between odd and even was already noticed by Domokos years ago, but not in a context like this. And of course, the folding can be multiple. So this is a simple example, a beam supported on three supports, and we see that we have 2 points of folding. Now let's go back to the shear bands, and I would like to mention something that I did years ago. I was analyzing this problem in my blackboard in my office, and then I said I would like to obtain a simple model for that. Why not to take, instead of 2 inclined shear bands, take only one? Then this shear band can be analyzed introducing a slider. A slider, it's an element which allows relative sliding but does not allow relative rotation and relative detachment. And then I said, since outside the shear bands the material usually unloads elastically, why don't we take those two materials as 2 elastic rods? And I sketched on my blackboard this elastic structure. I immediately understood something, that could have a bifurcation in tension. As an engineer, I was accustomed to bifurcation in compression, but that structure may have a bifurcation in tension. And so I decided immediately to investigate better this problem, and we solved it with the equations of the elastica. So we used the elastica for these 2 rods, and we imposed conditions for the slider, kinematic compatibility, the force is orthogonal to the slider, and the equilibrium of the slider itself. We have obtained this tensile bifurcation for theoretically, and we also decided to do an experiment. you heard something because the bifurcation, the post-critical behavior is unstable, and when the bifurcation happens, we hear a snap. And we see here the deformed shape of the elastic rod. On the upper row, there is a photograph taken at the end of an experiment. The slide there is very long because we wanted to see how things were going for very large displacement. And actually, a curiosity is that the shape of the elastic rod becomes identical to the shape of a water droplets because they are both governed by the same differential equation, the Euler-Elastica. One of my friends, Professor Fraldi, told me, you should find this instability in nature. And I told him, look, I have no idea where to find it. But he had this idea, and he was able to see that a mechanism like that operates in fingers leading to the so-called luxations. And we recently wrote a paper on that. Let's go back to the structures, and I would like to attract your attention on this structure, which has 1 degree of freedom, but it has 2 bifurcation loads, 1 in tension and 1 in compression. We will come later on this example because we will develop something here. And now I would like to move to another structural problem which has attracted my attention for at least 10 years, is the Ziegler double pendulum. We have 2 rigid rods which are connected through 2 elastic hinges. This system has 2 degrees of freedom. The peculiarity is that the load is follower and always remain aligned with that rod. This can be simply solved, and Ziegler did. And the interesting thing is that we have a region of Flutter, so this gamma is the dimensionless measure of the load. When we increase from 0, we enter in the Flutter region, and later, at the end, we enter in the divergence region. What is Flutter is an oscillation which, a sinusoidal oscillation, which blows up in time. So it's a sinus times an exponential. And what is the divergence instability is simply the exponential. So the peculiarity of this problem is that there is not a critical value, there is an interval. And Ziegler was able to demonstrate that this interval broadens if we include viscosity. This was called the paradox because seen from several points of view, I mean, as an engineer I would say, if to the same system I am adding viscosity, this will not help instability. So this was not expected, but was found by Ziegler, and it attracted a series of criticism. The most important was from Coiter, who wrote explicitly this statement: I propose the elimination of the abstraction of follower forces from the physical and engineering literature, because he thought this law does not exist, it's an abstraction, something for mathematicians, not for engineers. There were people trying to do their best to demonstrate the effect. George Herman, who was a big name, and Professor Sugiyama, a Japanese scientist, they tried to obtain the same effect with a fluid flowing through an nozzle, but they were criticized. People were saying, oh, but in that case there is a hydrodynamic term coming into play. Or Sugiyama tried with a rocket motor, but this rocket motor bursts in 2 or 3 seconds, and people said, oh, that's a variable mass problem, it's not the same thing. So we found our way through this problem, and I will not enter into detail because this was already published more than 10 years ago, together with Giovanni Noselli. This is our experimental apparatus. At low load we found stability, so the double pendulum remains straight. At a higher load we found Flutter instability, and when the load is even higher we found divergence instability. We had to add these 2 restraints because the first experiment we broke everything. That was the beginning, more than 10 years ago, but we wanted to analyze the elastic rod, and that required a complete new design of the experimental apparatus, which took 5 years of a PhD student. At the end of the PhD, he was declared saint. And this is the result. On the left, the experiment. On the right, the abacus simulation. This is the stable range where the structure remains straight. This is Flutter instability when the structure starts to dance. And we see divergence instability because the dancing happens at a lower frequency. That's the transition in the experiment. Why were these experiments important to us? Because we were able to put spots, experimental data on theoretical curves. And we were able for the first time to prove that the paradox actually looks not to be a paradox. It looks to be the reality. That was our first result, and then I decided to move on a problem which is very similar to that. Because in both cases we have a force which is non-conservative. So the Ziegler double pendulum is a non-conservative force, goes back to ideas from Bolotin and so on. This is also another structure invented by Russian scientist. The name is German, sounds German, but he was Russian, Reut. And again we have the double pendulum, but we have this T-shaped element because this load has to remain acting along a line. And so to do that, we need this element to still transmit the load to the structure, otherwise it would detach. So this simple load remaining along this line, it's a non-conservative load. And again, of course, we have the criticism from Professor Koiter, because he could not accept one and refuse the other, because they are more or less the same thing. So again, he said, I don't believe to this. And again, we had George Herman and Professor Sugiyama doing their experiment with an air jet impinging the structure. And even in that case, people said, oh, no. That's a problem for air elasticity. It's not the same thing of the Reut column. And so we found our way, because with our experience, we decided to use this new experimental apparatus where we have a freely rotating cylinder which compresses this structure, which is the Ziegler double pendulum. On the left-hand side, we see the simulation. It's a 2 degrees of freedom structure, so the simulation is straightforward. On the right, we see the experiment, which successfully gives us the Flutter instability. And again, we gave another independent proof of Flutter instability. Well, at that time, we had a new idea, because in our system, the force is always generated by a rotating something, which is a wheel, for instance, or a cylinder, which can freely rotate, and is constrained to slide against something, a conveyor belt, with friction. That was our idea. Then at a certain point, I said, what would happen if the friction would be infinite? Then there would be no sliding, and the constraint would become a non-holonomic constraint. So a non-holonomic constraint is a wheel which cannot slide, is a perfect skater. So non-holonomic constraints are constraints on the velocity, not on the position. This is very easy to be understood, because if you think to the skater can go everywhere, but during the motion, the velocity has to remain always in the direction of the skate. So I told myself, what does it happen if we include these constraints in our structures? Well, something strange, because non-holonomic constraints preserve the conservation of energy. And all these guys, including Koiter, of course, were writing specific statements pointing out that Flutter instability and so on is only possible because the loads are non-conservative. Now, if we found Flutter in this case with non-holonomic constraints, then all these people were wrong, included Professor Bolotin, who is still my idol. Okay? So we invented these simple structures, a triple pendulum to make things a little bit more complicated than Ziegler, with a skate constraint there. Instead of freely rotating wheel, the friction is infinite, so the wheel cannot slide. To load this system, we have to compress an elastic spring. there. And we invented this other system, which is similar to that, except that the load is a dead force applied on the left. Of course, the dead force comes from a potential, the springs come from a potential. We solved these examples and more. I'm only reporting two. And what we found is exactly the same Flutter instability, Ziegler paradox, Hopf bifurcation, limit cycle, everything happening for these systems in which the energy is fully conserved. This means that the belief that these instabilities were related to the fact that the load is non-conservative were a wrong belief. And now we can enjoy seeing a movie how these structures behave. I have to activate by hands. Oops, sorry. This is one example. We see that the system reaches a limit cycle almost immediately. So there are only a few increasing amplitude oscillations, and then the system reaches a limit cycle. This is the Ziegler type of behavior. On the right, the Reut type of behavior. Some initial oscillations, and immediately the system reaches a steady state. And at this stage, I came back to the idea of having a structure with a discontinuity in the curvature. So what is the idea here? I will try to tell you in a few seconds. On the left, we have a structure which is 2 degrees of freedom, a rigid rod, an elastic hinge, and there is also a longitudinal spring there that is fully visible in this sketch, because here the 2 points are almost superimposed. So 2 degrees of freedom, 2 elastic springs, rotational and longitudinal. The load is follower, so it's not conservative. So now imagine we have this system. This system has a Flutter instability, but the load in this case is 10 times lower than the critical load for Flutter. So this system is stable. Now the system in the center is the same structure, but the curvature of the constraint is negative rather than positive. So for the same load, the same stiffnesses of the springs, this structure is also stable. Now what we do is that we cut in 2 pieces these structures and we glue together to obtain this structure. What happens is something that, at least for an engineer like me, is surprising, because this is stable, but this is unstable. So then the question is why. So let's go step by step. We see the first structure. We have perturbed with a small initial velocity, and we see that the system vibrates, but the vibrations remain confined. It means stability. So the first system, positive curvature, stable. Now let's look at the second system. Second system, initial perturbation, oscillations. The oscillations remains bounded. Result, this is a stable system. And now, let's try to write down the equations for the third system. To write down the equation, it's just a matter of a student. It's not difficult, because we have 2 systems which are smooth, and they are jointed at a point. So we have a system of equations like those, which holds true for one branch or the other branch. For people like me accustomed to elastoplasticity, they look a little bit like the incremental equation of elastoplasticity. But anyway, I don't want to anticipate anything. The problem is how to analyze this system. It's very complicated. And we needed a guide, and we were able to find a book written by the nth top-level Russian scientist, Filippov, who wrote a book on these kinds of problems and gave us some hint how to mathematically treat it. So this book is very complicated. For me, it's the limit of my possibility. And so what I did, I told my students, because we were able to manage to demonstrate that the structure was unstable. But I told my student, I want to understand why. So give me an explanation that an engineer like me can accept. And they showed me this graph, which is, I have to say, very clever. We have a solution which is sketched blue. It is dashed there, it's continuous there. The blue solution is the solution with the negative curvature, the structure with the negative curvature. It is stable, and in fact, these oscillations remain bounded. And then we have another solution which is sketched red, continuous line and dashed line. It is the structure with the positive curvature stable and the oscillations remains bounded. But when we combine together the solution, it happens that initially we start with the blue solution, but then the solution becomes red, and then blue, and then red, and then blue. And when we put all together, we found a curve which exponentially blows up like that, because the structure takes the two solutions to grow up. And in fact, this is the linearized response we were able to integrate, and we see the interplay between red and blue solution to provide a blowing up instability. I asked my students to do the same thing for the nonlinear case, and the nonlinear case looks much more complicated, but nevertheless the mechanism is always the same. There is an alternance between blue and red, and eventually the system blows up, and we see here the instability of this structure where an initial velocity and initial oscillations blows up instead of decay. So the message here is too stable may make one unstable structure. And there is also another hidden message, which is clear to a guy like me, because for 20 years I have worked in elastoplasticity. In elastoplasticity, when we analyze stability, we are accustomed to think in two ways. We take the so-called Hill comparison solid, which is the plastic branch of the constitutive operator, and we treat it like an elastic law, a linear law. And also we consider the elastic branch, but we consider them separately. We are doing the same thing with the two structures. So we consider one structure and the other structure. But we know that when we put these two together, we may have instabilities which completely escape our analysis. And the structures and the solids, I have spoken a lot of structures, but I told you that I like solids. My structures are stupid, are not intelligent. I don't want to introduce any intelligence in my structure. I think that intelligence is only human. So all humans should improve their intelligence. Machines and structures should be stupid, because they have to behave exactly like slaves, as we wish. Okay, so how to link structures to solids? The problem is to implement these instabilities in solids. Use homogenization theory. So our approach was to take a two-dimensional elastic grid. This grid is periodic, is loaded through axial forces, and our goal was to homogenize this response. The equations for the rods are standard. I will not tell you because it's something for students. Kinetic energy, elastic energy, standard equations. Stiffness matrix. Of course, the stiffness matrix depends on the state of pre-stress. Fine. The only interesting things could be how to implement the periodicity. It is the so-called block wave or Floquet theory, very popular these days. Put together all these elements, we arrived at the dispersion equations. What to do with this? For instance, to produce dispersion diagrams. My students were happy. When they showed me this, I remained cold, saying, so what? And they said, oh, we can do many things. For instance, we can do something in the metamaterials. It's another far west of science, right? The guy who shoots first wins. What we did was to consider an infinite grid of elastic rods and to pre-stress a layer of these rods. That was our idea. Why to pre-stress? Because the pre-stress can be applied and removed very quickly. Actually, this is an old idea that we had together with Sasha Movchen and Massimiliano J. What does it happen? For instance, with the right pre-stress, we can obtain total reflection. A wave arrives and completely bounces back. Or we can obtain negative refraction. The wave arrives like this and it refracts like that. And this produces flat lenses. We have a source here, and we found the image there produced by the flat lens. And we can also obtain and focusing of a signal, things that these days are very appreciated. But nevertheless, this was not my goal. My goal was the homogenization. So let's go back to the homogenization. We have a grid which is unloaded. We load it, pulling or compressing every element. And we want to homogenize the response for incremental response, which involves not only axial loads, but bending and shear. What to do? Periodicity, Bloch theorem, Cauchy-Born hypothesis, equivalent continuum. The equivalent continuum is an elastic continuum which is pre-stressed. So it has a first order energy density and a second order energy density. The second order energy density relates the increment in the Piola stress to the gradient of incremental displacement through a tensor C that we would like to identify. So we have two ways to homogenize. One is in statics, where we simply impose a matching in the energy at first and second order, or we have a dynamic approach, which is a sequence of asymptotics, much more complicated, but leads to the same result. It is the same thing. So before to show you results, just let me say something. Does homogenization always work? Of course, if homogenization means that the energies are the same, of course it does, because we impose that. But I'm saying something different here. I'm interested to material instabilities, to instabilities. So if the homogenization would work, the instability in the structure would correspond to an instability in the material. But this does not always happen. There are cases in which a microscopic bifurcation happens, which is in the structure and is not in the solid. And there are other times where the two things coincide. So the bifurcation in the structure coincides with a lot of strong ellipticity in the solid. So in this case, the homogenization does work. In this case, it does not correctly work from the point of view of instabilities. These are not my results, but are from Nick Triantafilidis, Pedro Ponte Castañeda, and John Willis. They proved all this already. So we faced this reality, and we did our examples. This is an elastic grid, blue elastic rods, connected through inclined elastic springs, linear. This is the unit cell. This is the homogenized pre-stress at first order, very simple and nice formula. And this is the second order, a little bit more complicated, but don't be afraid. All this can be done through Mathematica, so it's closed form solution. We have all the components of the elasticity tensor. And now we can plot the results. This plane P1, P2 are represent the two components of load in the grid. P1 is horizontal, P2 is vertical. And this purple domain is the domain of stability. Well, for it contains the zero, of course, when the structure is unloaded, it is stable. And if we stay inside this domain, everything is stable. When we hit the boundary for a given loading path, in this case, homogenization works perfectly. And we have simultaneously a macro bifurcation in the structure and a loss of strong ellipticity in the material. In this case, where we have changed the stiffness of the springs, things go differently because there is a part of the boundary where homogenization doesn't work well. Because here, when we hit this boundary, we have a micro instability occurring in the structure, and the solid remains completely unaffected. So the solid doesn't see this instability. But we know when this happens, and so we can design this material to produce these instabilities. So loss of strong ellipticity means shear band formation. And you might tell me, but we don't see any shear bands here. Of course, to see the shear bands, we have to do something. And this something is to perturb the body. The concept of perturbation that we have developed in the last years was to perturb the solid with a concentrated force. So we need a green function. And we found these green functions years ago with John Willis, that for usual continua, not higher order or so, it's the maximum that one can do, because it has the material behind this formula has no symmetries at all. It's the most generic material. So we have this, and now we perturb. On the upper line, we have a finite element results, which were obtained by Giorgio Cardo, but it's not true, but Luigi Cabras. Luigi Cabras, a guy from from Cagliari, who did this finite element simulation in which there is a very fine grid of elastic rods perturbed by a forced dipole, two equal and opposite concentrated force. And the pre-stress is increasing from 0 up to a value close to the border of ellipticity loss. And the lower row is the same thing that done on the homogenized material with a closed form green function solution. What do we see? We see that when we are at no stress far from the border of ellipticity loss, we see almost nothing. These are the incremental displacement. But when we approach the border of ellipticity loss, we see shear bands appearing. And the simulation and the analytical solution are pretty close because in this case, homogenization works perfectly. So we can conclude that we have a tool to design architected materials which will manifest shear bands and instability at our desire. When we will desire to have these instabilities, they will do that. So imagine to have a piece of this material in your hands, you can squeeze it and see shear bands popping up, then you release it and it bounces back because all this is elastic. Well, people might ask me, the stability domain is open. Why? Because instabilities in beams occurs in compression, not in tension. In tension is open, this is unbounded. Well, but this is not true because we know that structures might buckle in tension. And so if we insert a slider inside the elastic rods, we found that now buckling in tension may occur. And so we found a stability domain which is closed in the stress space, which means that we can engineer failure. So we can design a material which will fail when we desire. And now I'm moving to the very last topic, the last thing I will tell you. So we have a grid of elastic rod. It's a little bit strange, but it is loaded by microforces. They are shown red. These microforces are follower. So they break the symmetry of the system. They break the conservation of the energy. They are the same forces of the Ziegler double pendulum. What does it happen when we homogenize this? Well, the microforces enter in the machinery of homogenization. They are crunched, and they give us the response of a solid. When we perturb this solid, in the upper row, the defined element simulations from Luigi Cabras. On the lower row, the closed forms result of the green function and the homogenization. They give the same message. What is this? This is Flutter instability in a continuum. It means that now we have a pulsating dipole here. So these two forces are pulsating in time, and they emanate waves, but these waves do not decay. They do not remain constant. They blow up in space. And so in the picture we see them far in the points which are at a higher distance from the source, because all the rest of the picture remains black, remain obscured by those waves. What does it mean? To have something like this, the acoustic tensor has to be unsymmetric. And in fact, we broke the symmetry through the introduction of the follower forces. We broke this symmetry. And so what does it mean that the acoustic tensor is unsymmetric? It means that the elasticity is unsymmetric. So it does not have an elastic potential. So the last thing I've shown you tells us that we can invent materials for which the elastic energy does not exist. It means that in a closed strain cycle, we can generate energy. How? Because of the microforces, of course. We are taking from somewhere. We are not inventing the energy. But this opens a new possibility in elasticity, because the last 200 years of elasticity results were almost all based on the concept of elastic potential. We can prove a lot of new theorems if we abandon the idea of elastic potential. And there are already people who are at work. My friend Alain Goreli has recently published a big, thick paper on this, in which many theorems, classical theorems of elasticity, are generalized for elasticity which is asymmetric. And the idea behind my, this is confusion, my ERC advanced grant beyond is exactly this. The idea is to try to build new materials which apparently break the energy. Thank you.